We will be starting now with the first of our science session. And as I said in the morning, it will not be a silo session, just one research area presenting. So what we did, because it was successful last year also, we just have a topical session, and there happen to be 2 research areas behind it. But you can figure out yourself who these research areas are, so we don't even tell you here in the session title. But before we start with that, there is a short announcement. If you have a poster that you want to present in the PICO presentation later on today, you can send it to Alistair if you do it before lunch, right? So now the session is led by Matt Salter and Christopher Landa, and it's called Earth Surface Atmosphere Interactions, Physical Processes, Changes and Their Impact. And I'll happily lead over to you now. Thank you.
Hello everybody and welcome. It's really cool to see the room so packed. We need a bigger room, huh? So it's great to see you all here. As Nina just said, Christopher and I are going to host this session. Earth surface atmosphere interactions, physical processes, changes and their impacts. Obviously this is a very, very broad topic. The reason for that is that we try to encompass as much of RA2, that is clouds, aerosols, turbulence and climate, and RA7 research, landscape processes and climate within our topic. I don't think I need to go into it much more detail than that. I think I will let the science talks do the speaking for this research. What I will say, I would like to encourage our speakers to project their voices out to the back of the room. You have a microphone, but it doesn't help anybody in the room. So that's to all of our speakers, cool. so that everybody can hear. I hope you can all hear me anyway. I would also say to the speakers, we have Jenny sitting here who's raising her hand now. She is going to raise her hand when you have 3 minutes left and 1 minute left. So, and we will be strict. There's a big sign there. So we want to have questions and some discussion. So if you can abide by those times, that would be really great. Mm-hmm. But otherwise, welcome to the speakers. And our first speaker, Dominic, who's going to talk about from a polar to a marine environment, has the retreat in Arctic sea ice led to a shift in aerosol optical properties? So, welcome.
Yeah. Hi guys. So this was my master's thesis work at ACSL, and I'll take you through. So I'm sure many of you already know what aerosols are, but just to give you a brief introduction. Okay, so they're defined as any liquid or solid particle suspended in a gas. And they can range from a few nanometers up to a few micrometers. And then we can split them into coarse mode or fine mode depending on their size. So typically this is between 1 to 2.5. And I've got a range of pictures here. You've got some anthropogenic sources, some primary sources, so emitted directly into the atmosphere. You've got anthropogenic and secondary, and then we've got natural and secondary. And then I'm going to place close attention to the example in the bottom right, and that's sea spray aerosols. This is produced from wave action, and this is natural and primary. And these aerosol particles, they can be removed via wet deposition. So that means they serve as a cloud condensation nuclei, and then they're precipitated out, or by dry depositions in the absence of precipitation. So they have a significant impact on the Earth's climate, either through direct effects, so that's scattering and absorbing light, and also indirect effects. But I won't talk too much about it, but you can see here we've got the radiative forcing based on the uncertainties, and overall aerosols are considered to have a cooling effect. Over in the Arctic, they're considered to be, or there's a renewed interest in aerosol science in the Arctic as a means of explaining the last 25 years of increased warming, known as the Arctic amplification. So one consequence of this is the retreating of the Arctic sea ice. So I've got up here sea ice concentration in 2000, and then the blue 2016. So it's been a dramatic retreat in Arctic sea ice, which has led to more open ocean. And this open ocean means the ocean is in contact with the wind. And so there's been perhaps a production or an increased production of sea spray aerosol particles. So, and these are defined as coarse mode particles. So they're on the larger end of the size distribution. So I can ask the question, research question, has this retreat led to a shift in aerosol optical properties? And for this, I used observation from Mount Zeppelin Observatory, so I'll take you there now. So this is it, and it's located on the western edge of the Norwegian archipelago Svalbard. Its remoteness and its high altitude means that it can sample pristine Arctic air, and it's also part of this global atmosphere watch. There's 30 other sites across the globe. So air's taken in through the inlet here, the Holer Inlet, and then it meets this device instrument, the nephelometer, and this is quite a standard piece of kit. It can measure light scattering, so aerosols come in, light is scattered, and then via the filters we can measure the scattering coefficient, the backscatter coefficient at 3 different wavelengths, and then we can get these other parameters. And this one is, I'm going to touch on, is important, the angstrom exponent, and it's a, so we know the scattering is dependent on the wavelength, and from this essentially all you need to know is that the angstrom exponent in this power law, we can use it as a proxy for aerosol size. So essentially small angstrom coefficients, exponents, and you get an aerosol that's dominated by coarse mode, and then large angstrom, we have an aerosol dominated by fine mode particles. Okay. In conjunction with the optical data, I also used back trajectory data. So this is a high split model that uses meteorological data to track aerosols back in time from their arrival point. And from this we got a range of variables, including the mixing depth. So this is the, we can use this to look at the height of the mix layer, which is important. So the mix layer is well mixed, and it's where the aerosols are emitted, and it's the area of the atmosphere we're interested in. And then using the satellite-derived sea ice concentrations, I could get the time, the trajectory spent over ice, land, and ocean. So I'll give you an example just to show you what I mean. So this is one trajectory out of thousands, and we've got the trajectory arriving at Svalbard, and it goes back in time, and the blue represents the ocean, the green the land, and time over ice by the pink. Okay, and then I could also look at the PBL as well. So the time it's spent in the PBL, the green, and above. So some results. I've got the annual cycle here. So this is fairly consistent with previous studies. You've got the Arctic haze phenomenon here with the increased scattering coefficient in late winter, early spring, and then increased precipitation, and it's more localized during the summer, and the scattering coefficient goes down. And then for the angstrom exponent, down here we've got fine mode particles are dominant in the summertime, as opposed to more coarse mode particles in the winter and autumn. So where are these particles coming from? From this source mapping that I produced, you can see it mainly coming from Russia and East Asia, which is fairly consistent with a lot of other studies that suggest that these scattering-inducing particles are coming from these areas and being transported up to the Arctic. And then looking at the angstrom exponent, we see this west to east gradient. So the coarse mode particles originating from the North Atlantic and the fine mode from the Eurasian landmass. So I had 17 years worth of data, so I could do some long-term trend analysis, and there was a statistically increasing trend in the scattering coefficient. So more scattering-inducing particles. And then for the angstrom exponent, there was a clear negative statistically increasing trend. So from this, the angstrom exponent is decreasing, which means that there is, or it indicates an increase in the coarse mode aerosol particles, and could this be the result of sea spray? So common coarse mode particles in the Arctic would be sea spray or mineral dust, for example. So what I reasoned that there were about 4 reasons for this. So either, as I suggested earlier, so you've got more open ocean, increased production of sea spray, and then this also leads to a shift in the aerosol composition? Or could it be changes in air circulation, so that North Atlantic or the air over the North Atlantic reaching Svalbard, carrying the sea spray aerosols? Could it be changes in wind speed? Or could it be a decrease? So the opposite is a decrease in the fine modes. These are anti-correlated. For this, just remove it straight away because we've seen an increase in the scattering coefficient. So it's unlikely to be as a result of this. And then for the retreating Arctic sea ice, well, first to test this, I wanted to see if air masses were spending more time over the ocean. So if we look at the entire trajectory, so this is the median time air masses spend over land, and that doesn't increase. So air masses aren't spending any more time over land, but ice is decreasing and ocean is increasing. So this is probably a result of the retreating sea ice. However, if we look at the PBL, or within the mixed layer, the trajectories within the mixed layer, we see that there's no, so this is the bottom one here, there's no significant change. So the trajectories as a whole, we see this change, but then within the area we're interested in, there's no change. And if we compare the angstrom exponent to the relative residence times, we see the angstrom exponent over land is quite high, an indication of the fine mode. Similar with ice. However, for the ocean, we see the angstrom exponent is dependent on its time over ocean. The more time these trajectories are spending over the ocean, the lower the angstrom exponent. So the angstrom exponent is indicative of, or the time over the ocean is indicative of a low angstrom exponent. So course mode. I looked at the direction the air masses were coming from as well, and you can see that the low angstrom exponents here, so the ones dominated by course mode, are coming from the west. So these are the ones coming over the ocean. So you've got quite a course mode southwesterly and northwesterly. And then I also looked at how these changed over time, how these changed over the 16 years of data. And I saw an increased contribution from the west as well. So more westerly air masses arriving at Svalbard, bringing those course mode particles. The angstrom exponent was also dependent on the wind speed. So the average wind speed along the trajectories meant that they could transport and produce these course mode particles and bring them to the Zeppelin Observatory. And there was an insignificant an increase in the wind speeds over the 16 years as well. So in conclusion, the trends, I showed there was a statistical increasing trend in the scattering coefficients, decreasing trend in the angstrom exponent, and meaning more course mode particles. And then for the trajectory analysis, we've got a range of factors. So we've got the ocean, time over ocean was indicative of a more course mode dominated aerosol. Wind speeds were increasing slightly, and also indicative of a low angstrom exponent. And then there was more contributions from these westerlies as well. So could I answer my original hypothesis? Not exactly, no. But then I showed that it was probably a variety of reasons, and further work needs to be done in targeting the area and looking into more detail as to where these air masses are coming from and so forth. But thank you, guys.
So thanks, Dominic. That was great timekeeping there. Do we have any questions from the audience?
Yeah.
Thanks for the nice talk. I was wondering, can you distinguish between the effects of the air masses spending more time over the ocean or just a change in the circulation regime. I mean, what you show is that you have more trajectories originating from different areas, or not more time of the ocean. So you have more trajectories coming from a different part of the Arctic than or a change in source region over the time. And you also have a change in the amount of Arctic sea ice, right? So, but how can you distinguish between these two effects? So one would just be a pure dynamic effect. So you would just change the circulation. Whereas in the other case, I mean, you say it could also be just the recession of sea ice that could cause the increase in these aerosols.
Yeah, I think that's the problem, separating these two influences. But I also looked at I ran this with a fixed sea ice, for example, and noticed decreasing trend in time spent over ice as well, but not to the extent that you see with the changing sea ice concentrations as well. But yeah.
Okay, I think there's time for one more question.
How are you quantifying wind speed change? Is it just local wind speed, or
no? It's not surface wind speed. It's wind speed that you get from. So the high split model produces. It gives you the distance it travelled, and from that you can calculate an average wind speed based on. Yeah, they were 10 days. So, yeah.
That was a quick question. Maybe one more.
I was just wondering whether this change in aerosol properties would lead to higher or lower warming feedback on Arctic amplification.
So, I think there's a lot of. I'm not the best person to answer that question, but I would suggest you've got more. If you've got more sea spray aerosol particles, they're quite important for CCN. So, I'm not sure. But perhaps, maybe an increased warming. I don't know. But they scatter a lot of light, so yeah.
Okay then, I think that we'll move on to our next talk, and let's thank our speaker again. It's not ideal. Okay then. So it's a pleasure to welcome Lena Gordon, actually the director of the Stockholm Resilience Center, to present moisture recycling and tipping points in tropical forests. So when you've got your hair sorted.
Thanks.
Welcome.
It was complicated actually. Let's see, is it on? Okay, good. Thanks. Thanks a lot for letting me present on this topic here today. Even though they're not acknowledged here on the first page, I have everyone on the last page, but I really want to say thanks to all the contributors to this presentation, because in reality I'm having the presentation, but it's really work done by some of the younger researchers at the Stockholm Resilience Center and elsewhere, so especially Landvang Erlandsson, Ariesdal, who I see now is in the room here, so all technical questions go to him. And then Patrick Keys, that's also been working with us. But for different reasons, they couldn't do the presentations. I'm giving it now. But why is this interesting? I think it has not been anyone who could have missed the attention on the Amazon this year, and all the headlines that the deforestation and the increasing rates of deforestation and the big wildfires that are happening in the Amazon right now. Just 2 days ago, new data came out showing that the Amazon deforestation is peaking. Again, the largest numbers in a decade for the Amazon. And what everyone is worrying about, of course, is that are there tipping points where the deforestation takes place and there is no capacity any longer for the rainforest basically to return, and we're therefore losing a lot of the ecosystem services that the forest generates. So this idea of tipping points in rainforests have multiple backgrounds, but I think this paper by Hirota et al. In Science in 2011 shows some of the background and also how it's related to rainfall. What they did in this paper is empirically look at forest cover in relation to rainfall. And they did that across different continents and also intercontinental data. And what they could see is that it seems to be clustered, where you have at higher rainfall levels, you have one clustering of high tree density, and at lower levels you have another clustering. So you basically get these different regimes, and that there are then tipping points between them. So in some precipitation levels you could have either forest or savanna or grassland state, but in the extreme areas of precipitation you only get one of the systems. So one question is, of course, are we now, both through climate change and deforestation, reducing precipitation levels to a stage where the forest will have a difficulty in returning? So I and some of my collaborators have for a long time been interested in the idea of moisture recycling. And moisture recycling is basically just how much of the evaporation that's returning to rainfall. And we're particularly interested in how much of the evaporation from land and land-based ecosystem that then return as rainfall over land. And to what extent can we, through land use change, alter this feedback between land and rainfall. We also pioneered in a few years ago the idea of precipitation sheds. Basically that if you have a sink region, a specific area, where does actually the rainfall come from for that area? And then we mapped out, so you can think about these precipitation sheds basically as sort of watersheds of the sky. So where does the rainfall come from that falls in these areas? I think globally around 40% of the rainfall comes from previously evapotranspired over other land surfaces, while the rest come from the ocean source areas. Just to give a very concrete example, here you have the precipitation shed for the Sahel region. So the yellow circled area there is the sink region, where we looked at the precipitation and then looked at where does that moisture come from. And as you can see, it comes from much larger area than just within that specific region. So the idea of this kind of moisture recycling as a source of rainfall in the Amazon has triggered a lot of different research. So here's by Landvang Erlandsson contributed to this article, but it's led by Delphine Semp at PIC. But they looked at the cascading effects of moisture recycling through the Amazon. And what they were particularly interested in in this paper was to say, what if the influx from the oceans would be decreasing? How would that hit the resilience of the forest further inland because of these cascading effects of moisture that keeps re-evaporating and falling as rainfall? They ran different scenarios to see to what extent could sort of a substantial reduction of influx of moisture from the oceans actually contribute to deforestation or vulnerability of the rainforest. And they also mapped that spatially. So what you see here is two different scenarios, one with the last glacier maximum scenario, and the other one, I'm worried talking with this climate crowd, but and then the other one on the end of the 21st century scenario. The crosses there are where areas are currently deforested. And then you can see how much areas that could potentially have much lower tree cover. And then you see the loss in resilience in different places of the forest if you have these dramatic shifts in influx of moisture from the ocean. Another paper led by Arias Dahl here in the room was looking at the role of also these forest rainfall cascades and how they especially buffer against droughts across the Amazon. And they've shown that if you look at monthly rainfall of oceanic origin and compare that of how much of the rainfall that comes from transpiration recycling ratio, it is actually at the very low contribution from the oceans. You have very strong contributions from transpiration to the overall rainfall. And then they looked at where in the Amazon then are different places particularly dependent on this transpiration recycling. This first figure shows the areas of rainfall, how much of the rainfall that comes from Amazon tree transpiration. And as you can see, it's primarily in these southwestern areas and north areas of the Amazon that have a particular strong contribution of moisture recycling. So they also developed an index of sort of how resilient then are these different places to loss of the transpiration recycling ratios. And as you can see here, there are particularly the areas also in these places that have the largest risk of losing resilience if these functions are being reduced. And here's another map sort of showing which areas are contributing most to the resilience of the Amazon. And as you can see, the areas that are particularly contributing to the Amazon region are primarily in the southeastern part. And these are also the regions that currently are at the highest threat of deforestation. So they are particularly important for the resilience of the Amazon. Some of the key conclusions from that work is that up to 60-80% of the Amazon in some regions of the Amazon originate from terrestrial evapotranspiration, and that retained transpiration helps buffer against droughts especially, and that disruption of these moisture flows can lead to this sort of self-amplified forest loss. And also that in the Amazon, especially in dry years, there is a stronger forest rainfall interactions. So one of the things that I and Landwang Erlandsson have been trying to do is to look at the comparing kind of the Amazon to the Congo rainforest area, because there has been so much focus on the Amazon and much less done on the Congo system in terms of sort of moisture recycling and deforestation. So we are also focusing in this work particularly at these dry years and dry periods and the moisture recycling that is contributing, especially in those times. Some of the data and models that we have been using. I'm not going to go through it too much, but here are basically the two then study regions. And what you see here is the precipitation sheds for these study regions. So where does the precipitation come from to the Amazon basin? And then the evaporation shed, which is basically where does the evaporation end up? So what are the regions that are contributing most to rainfall? And you can see that it's very similar patterns also to what's shown in this other paper when it comes to the Amazon region. So some of the findings that we have, and this is work in progress still, is that we also see this importance of forests as their own moisture suppliers, and that increases by 67% in dry seasons, and that dry years further amplify this role of forests as their own moisture source. We then looked at this potential risk of tipping points, and what we did then was to sort of do similarly to the Hirota paper that I showed before, to look at where seems to be thresholds where you either have a forest or not a forest. And we put the threshold that where 95% of the forest cover is. At what level of precipitation do we have that threshold? And we looked at both kind of how it looked in, especially in dry seasons, and then also annual rainfall. And this is what you can see for the Amazon. And then we looked at what if you reduce the this capacity of the moisture to self-generate rainfall. And as you can see, when we reduce that moisture generation, you also have a forest loss, potential risk of forest loss, because it then crosses its threshold. But what's interesting is that when we did exactly the same thing for the Congo, we could see that the risk of forest loss increased much more rapidly than for the Amazon. So you can, if you compare the graphs, the lower graphs here, for the Amazon region versus the Congo region, you see that you have a much more dramatic response to that. So in summary, basically, we think that the Congo seems to be much more vulnerable to this type of rainfall reductions. And that we can see that if we cut all this forest moisture supply, it would increase the risk of 90% of the forest in Congo, but only 30% in the Amazon. And also that dry year moisture recycling intensification seems to affect the Congo forest resilience even more negatively. So I think that's quite interesting, also thinking about how can we sort of expand some of the research that's now done in the Amazon also to the Congo region, and so we get a better and more in-depth understanding of also what's happening in Africa. So thanks to all the contributors to this talk, and thanks for listening.
Thank you, Lena. I think we have time for one quick question, maybe.
Thanks for your talk, Lena. Actually, my first academic paper was about the Amazon forest. So I was thinking about the differences in Amazon and Congo. Could it be like you have the Andes as a topographical barrier that actually stops the winds from passing through the area and giving more rainfall than if you compare to Congo? Could it be a possible explanation?
I'm not really sure, but I mean that is one of the reasons that you have the pattern that you see in the Amazon is sort of because of that reason. So, but I'm not sure exactly how much that is contributing, but it's a good thing to look.
I was just wondering how much you have taken stomatal densities into account.
The stomatal densities?
Yeah.
You mean the variation in the stomata? Yeah, I don't think
the entire water content in the atmosphere passes through stomata twice in a year, just in the tropics.
Yeah.
And with increasing CO2, the stomatal densities are decreasing.
Yeah.
And this has a acute effect on transpiration.
Yeah, exactly.
So I think you should take that into account.
It's a good point, but it's not something that we have estimated in the models. Yeah.
I think you should.
Yeah.
I think we just thank the speaker again. Okay, then I can now introduce our third speaker for this session, and that is Maria Burgos, who is going to talk about a new benchmark dataset of aerosol hydrogen, global view on the effect of water uptake on aerosol particle light scattering.
Okay, thank you, Matt. So I'm Maria. I'm working. Okay, this happened. But I think, do people hear me? I don't know if it's because of the glasses. Okay. Okay, maybe I can hold it like this.
Probably do you want to hold this one?
I think it's because of the glasses. Okay. So I'm Maria. I'm working as a postdoc at ACCL. And I want to present you the work of creating a new benchmark dataset of aerosol hygroscopicity. And I want to show you a global view on the effect of water uptake on aerosol particle light scattering. So this is me presenting, but I've done this work together with Paul Seeger, also at ACCL, and many other collaborators, mainly the site managers and providers of the data. So as the talk of Dominic, I want to go a bit through the aerosols and why are they important to us. And I want to explain you the measurement technique I've used and some of our results. So the aerosols are the solid or liquid particles suspended in a gas, in our case the atmosphere, and they can come from very different origins. So they can be natural as desert dust or sea salt or volcano ashes, and they can also be caused by anthropogenic activities like biomass burning from some agricultural practices, or the pollution coming from different industrial activities. So in my case, that I want to create a benchmark dataset, it's going to be important for me to measure as many types of aerosols as possible. They can be directly emitted to the atmosphere, so we'll call them primary, or they can be produced by reactions between certain gases, so we'll call them secondary aerosols. Their sizes may vary between 1 nanometer up to 100 micrometers. And the resident time in the atmosphere can go from few hours up to few weeks. And here it's an observation just to compare it with the resident time of greenhouse gases, as CO2, that can go up to 100 of years. So that means that if we want to measure with, we want to create a benchmark data set in the whole globe, we are going to face challenges in terms of spatio-temporal sampling and measurements because they vary a lot. So now, related to climate, they can have a direct effect if they scatter or absorb solar radiation. So if they scatter light, they will have a net effect of cooling the atmosphere. And if they absorb the solar radiation, they will have an effect of warming the atmosphere. And they can also act as a cloud condensation nuclei when acting as a particles on which water vapor can condensate. For me, the important effect I want to focus on is the aerosol hygroscopicity. So this means that the aerosol will be able to take up water, and thus is going to change its size and also its chemical properties. And this is going to influence on the scattering coefficient, that is this sigma. So the scattering coefficient will depend on the size and chemical composition of the aerosol, so finally on the relative humidity that we have in the surrounding air. This is important if we want to do climate forcing calculations, or if we want to validate remote sensing, or if we want to improve global climate models, for example. And here I present the scattering enhancement factor, that is the variable I'm going to be working with. And this is defined as the ratio between the scattering coefficient measured at wet condition and dry conditions. So I want to show the instrument we've used to make these measurements, and this is called the tandem humidified nephelometer. And there are two main systems I want to focus. So we have the PSI system, where we have two nephelometers measuring in parallel. So I don't know if it's showing the point. No. Okay. So we have one nephelometer measuring under dry conditions, and at the same time we have a humidifier and a dryer. So we will measure the aerosol scattering under wet conditions. So how does it work? We can switch on the humidifier and measure a different increase in relative humidities. And if we keep the humidifier on and we switch the dryer on, then we will decrease the relative humidity and measure the scattering again with decreasing values of relative humidity. So we will have with the dry nephelometer the dry scattering, and with the wet nephelometer the wet scattering, and the ratio between them will be the scattering enhancement factor. And then we have another system where how we can measure this. This is the NOAA system, and it's we have the aerosol. First we measure it under dry conditions, then they go through the humidifier and we measure them the wet conditions. And with this we have what we call the humidogram, and this is how the scattering enhancement factor varies with relative humidity. So some of the particles will grow or shrink monotonically with increases of RH, and we have the hydration and dehydration curve together. But we have one effect here that is called hysteresis. So some of the aerosols will increase the scattering, and then it will come a 3 minutes. Okay. A jump, and we'll have the liquid sense, and I will jump this. So there are several parameterization of the humidograms and several ways of overcoming this hysteresis curve. So there were several studies where the scattering enhancement factor was measured at different European sites, and what we've done is to get together 26 sites around the globe. Some of them were measuring long-term sites, and some others were measuring campaigns of only several months or less than a year. So we put all this together and we create a harmonized data set. Yep, and this is published here with all the co-authors in Scientific Data. So this is some example of the data. Here we can see some sites where you don't have any hygroscopic growth, like Niamey here. Okay, sorry for this. So this is our main result in the paper. We have the scattering enhancement factor, and it's larger for Arctic and marine sites. And the scattering enhancement factor gets lower for rural, urban, and it's almost negligible in desert sites. So if you go to EBAS in Nilu, you've got all the files and the data set we've created, and then you can search by or select a site if you're interested or a date, then download it and you will get a text file with a lot of metadata of how it's been created, the variables you've got in it, and the data. Yeah, so aerosols are important for us. We want to see how they scatter light depending on relative humidity. And we have created a standardized benchmark data set with measurements from 26 sites. We have shown that Arctic and marine has the largest increase in scattering, and the lowest is found in desert sites. And we have a work in progress where we are comparing this data set with global climate models. If you want to know more about this, you can pop by the poster. And thanks for your attention. But I've got 9 minutes here.
Yeah. Okay, I think we have time for one quick question, if there is one in the audience. One?
Okay, this may be a detail, but you express this very much as a function of relative humidity. And I just wonder, why did you select relative humidity and not, for instance, vapor pressure deficit? What type of difference do you think it could do?
With pressure, sorry?
Of vapor pressure deficit, if you should look to drying power, the moisture can be expressed in so many different ways. But relative humidity is, in my view, not the most precise if you should look to the transport, since it depends on the temperature, it depends on the pressure.
So, again, please, one here. So all this came because the measurements were made at dry conditions. So the way we had to increase easily the relative humidity was with the humidifier. So we wanted to see the difference between dry and wet, and that was like an easy way to get it, to dry them and to humidify them. So it was a compromise between what you can get of dry and wet. And the ease of getting the measurements, because these measurements happen in many sites, and the instrument that we had was this one, and it worked with this. So I guess it was because of instrumental constraints maybe that this way was chosen.
Okay, I think we have to move on, but let's thank Maria again.
Okay, then we welcome up Anna Skaini. Anna will talk about agriculture productivity through the lens of hydrologic function.
Thank you. Sorry, too many here as well. Okay. I suppose. I'm sorry. Okay, so this work is part of my postdoc project, done with the support also of the Bolin Center, and in collaboration with all these lovely people that you see listed here. Okay. Keep it. Okay, so we are changing a bit the focus here. So my talk will be about agriculture and hydrology. And I will start with a little bit of introduction about this. So yield is the main measure for agricultural productivity. And we can see here in the main graph that for a given evapotranspiration rate, we can have a range of different values of yield. You cannot see the pointer. Oh, I don't know. It's disappeared. So yeah, on the y-axis you have a range of values there. Thank you so much. And these depend on increased nutrient availability. In the same way, there is also a relationship between the nitrogen input, so in these two graphs, and the crop yield. And in both cases, these depend on go up to a certain upper level. So with that in mind, nitrogen use efficiency is the measure of crop harvested product divided by the main nitrogen inputs that are the sum of fertilizer, both organic and inorganic, the agricultural nitrogen fixation, and the nitrogen deposition. So we know that about 20 to 50% of the applied nitrogen can be recovered. So only up to 50% of what we apply can be recovered at crop. And this is due to different causes, among others, the volatilization, the nitrification, and leaching. In this talk, we're particularly interested in leaching because leaching is the process that is more linked to hydrology in that it depends on the percolation of water. And we can expect that crops that use better the water that they have available will leave the soil less prone to leaching. So with that in mind, what we try to answer here is how, if and how, hydrologic conditions affect nitrogen use efficiency. So to do that, we use two main metrics. One is the nitrogen use efficiency that I have already presented, and the other one is the evaporative ratio. Evaporative ratio is the ratio between the evapotranspiration and the precipitation. In this, for the purpose of this talk, we are actually using a simplified version of the hydrological cycle, and this works under the assumption of long-term data. Therefore, we will use annual data during all the talk. And in this case, we can assume that the evaporative ratio is equal to 1 minus the rainfall divided by the precipitation, the runoff divided by precipitation, which is the runoff coefficient. So our expectation is that nitrogen use efficiency scales with the evaporative ratio. So to
To do this exercise, we focus on catchment scale because it's the unit of the hydrological unit that we all know. And we will put our effort into catchment comprised in the conterminous United States for two main reasons. One reason you can see here is because the US is a very big country and it encompasses different climates. So interesting case study. The other reason is because of data availability. In particular, here we need a lot of different data, all the data that I presented before. And in order to do that, we need to search for this data, and that was quite a difficult exercise. And therefore, in this case, we are trying to focus only on the period between 1987 to 2007. So only a few years of data compared to what we can catch for instance, for climatic data that are much longer. And we will focus on 73 catchments and comprised in wet and dry climate. So in the graphs you will see blue. Everything on the tones of blue will be wet climate. Everything in the tone of orange will be dry climate. And we will also cluster the data according to how much they are agricultural in percentage. More than 50% on the darker color and more under 50% in the lighter color. So I will skip most of the methodology, which is very long. Please ask if you need more information. But we have two main types of data. Either the raw data can be either raster or county data, so county level in the US. And so we have two different methodologies to get all the data in the same scale, both temporal and spatial. So all the data at the end are catchment scale and annual data. So for this presentation, I will test two main hypotheses. The first hypothesis is that nitrogen use efficiency is correlated positively to the evaporative index. And if the correlation is positive, then our hypothesis is supported. For the second option, for the second hypothesis, we actually divide our time span into decades, and we compute the nitrogen use efficiency and the evaporative index for each of the 2 decades. And then we divide decade 2 divided by decade 1, and we check what happened across the decades. And this is done test if there are consistent changes through time. So we want the data to fall into the 2 light blue squares here. Okay, so let's check our hypothesis. Here you will see a sketch always at the bottom right of the screen. And so the data for the first hypothesis, well, like this. So this is not my favorite graph because we see that there is no actual linear relationship. You could think that maybe there is a relationship if we check the dark blue points, but actually there is nothing significant here, even if I try to cluster the data differently or crop by crop, etc. Nothing super striking. But let's see what about hypothesis 2. So for hypothesis 2, things get more interesting, because we can see that most of the catchments fall in the upper right corner. Square. So overall, both the evaporative ratio and the nitrogen use efficiency increased over the second decade compared to the first one. This is true mostly, particularly for the wet catchment, where you can see that they fall in that particular square. Another thing that we can see here is that some catchments are outlined in black, and those are the ones for which more than 10% of the area is irrigated, of the agricultural area is irrigated actually. And we can see that those are a little bit weirder, which makes sense because they are irrigated, so they're not relying on natural rainfall. And for those, there is a lower increase in both evapotranspiration, over precipitation, and nitrogen use efficiency. So now we plot the same data in a little bit different way. So we try to see how they plot as box plot. So always decade 2 divided by decade 1, and our ratios there. So we see that overall all the data are above 1, or most of the data are above 1. So they're raised in the second decade. And if we try to see how the components of these ratios are behaving, then we can say that temperature, which is not included in our in how we estimate the evaporative ratio, but is a very important part of evapotranspiration. Temperature has increased for all the catchment in the second decade compared to the first one. Not even one catchment has, some are close to zero, but they're mostly increased. And that is very interesting. So we expect a higher evapotranspiration overall. And that is paired with a lower runoff, even though runoff is not significant. On the other hand, we see that for the components of the nitrogen deficiency, the fertilizer is not statistically not significant, but it's all over the place as well. And there is quite a strong increase in yield here. And overall, the nitrogen input has increased because of two factors. One, nitrogen deposition that is slightly increased, which is common for the US. It's a known thing. And the other one is that there is more soybean nitrogen fixation. So with that in mind, we try to conclude a little bit, and we remind ourselves of our hypothesis. We try to see if there is a correlation between the two metrics that we are testing across 20-year period that we're tracking, and there is none. And as for the second hypothesis, we can see there is a certain relationship between the two, and that mostly, overall, we see an increase in both metrics in the second decade compared to the first one. Now, if we try to put together the information given by our components, then we can say that there is for the hydrological cycle, there was a higher EP compared to the first decade in the second decade, and that there was a decrease in runoff. That suggests us that there was a decrease in leaching, if you think of what we said at the first part of my talk. That was combined to, for the nitrogen use efficiency component, to nitrogen input increase, particularly driven by the soybean nitrogen fixation, which then led to a very high overall increase in yield. And so there is a feedback between what is the crop choice. In this case, an increase in soybean nitrogen fixation means that there was more soybean cultivated, and climate-driven change, or an hydrological change, given by the increase in temperature and the decrease in runoff. So there is this feedback between farmer choices, as they say, and hydrology, and also climate change, because we know that hydrology is actually driven by mostly climate, and there is climate change going on. Thank you very much for your attention.
Thank you, Anna. We have time for a couple of questions.
I've been looking a lot to leaching, nitrogen leaching from Scandinavia, and there's no correlation between runoff and leaching. You don't get more nitrogen leaching because you have a higher runoff. Leaching seems not to be coupled to the hydrology in itself. It's more, on my view, the demand and the supply of nitrogen by itself. So water is of course a carrier of nitrate, but normally it's not the water that makes sense for the plant efficiency in the uptake. So my view is that the fertility and the internal transformations in the soils.
So soil retention, you mean?
Do you comment on that?
Yes, I didn't study Sweden yet. I think it's one of my next chapters. Yeah, well, I can say that for sure there is a relationship between the soil structure, soil retention, and many other processes that happen in the soil with relation to leaching. So leaching is not only given by runoff. So I'm perfectly in accordance with what you say. Here I'm simplifying things a lot, of course. Also, I'm using very big areas, so I try to use the soil as well, soil map, to try to see if there is a relationship also at catchment scale. It's a little bit tricky because the catchments are a bit big, but it's definitely not the only thing, of course.
definitely, I mean, the decreasing runoff is quite interesting in itself, right? Like climate-wise, especially paired with the increase in temperature. But obviously also the fertilizer. Here they over-fertilize everywhere. So I don't know in Sweden, but in the US definitely. I can tell. Thank you.
Okay, thank you. We have a short urgent question.
But the leaching wastes nitrogen that the plant can't use, but so does the sort of denitrification and release to the atmosphere. And so how do you, in terms of figuring out what's determining the yield, how do you know that it's not the atmospheric part that's actually having a big effect on also from the standpoint of the risk that farmers' choices are just trading one kind of environmental harm for another, because N2O is pretty awful for the greenhouse gas problem.
Yes.
So, I mean, is there any estimate of how much the atmospheric loss is how significant that is as a factor in how the crops use nitrogen?
Thank you. So that's a very good question. In this analysis, we are not taking into account this type of processes. We are only taking into account the nitrogen deposition as an input. So that's it. But very simplified again. So it works for certain areas probably, and we might have some error because of denitrification or volatilization for sure. Yeah.
Okay, thank you, Anna. If people have more questions to her, you can talk in the break. So our next speaker is our last speaker before Imen Åhlén. She will talk about wet landscape size threshold for ecosystem service delivery, evidence from the Norrström drainage basin in Sweden. So,
thank you. Hello everyone, my name is Imen and I am a PhD student here at the Department of Physical Geography, and together with my supervisor I've been working on wetlands and specific wetlands with this title, a work that actually got recently accepted. So, what about these wetlandscapes? Well, this is a different perspective of working with wetlands. So usually we look at wetlands as single units and we understand them like that. But here, previous studies suggest a shift in studying them. So looking at them in the landscape as hydrologically connected wetlands. And in fact they are, even though we might hear the words talking about isolated wetlands, as a matter of fact they are connected through the groundwater system and so on. And so why is this scale interesting? Well, because we value wetlands and we see them as a large-scale nature-based solution, and because we face climate change and other type of land use or large-scale changes like land use changes, it might be interesting to look at the aggregated unit of wetlands in the landscape and to see, well, how will they be affected by these changes that we face today. So there are some questions we have been asking ourselves, and first of all we then took and looked at wetlandscapes in this basin, the Norrström drainage basin. That actually, so this basin drains out through Stockholm, and it's one of the basins in Sweden that is an important emitter of nutrients, for instance. And also why we use this basin is that, well, here we know there's some data and previous studies on this basin. So as you can see here, we have 15 different wetlandscapes, different sizes from 1 to 15. They are ordered by size. They differ, well, as I said, in size, but also in terms of the amount of wetlands and wetland density. So what did we do? Well, we wanted to quantify characteristics important for ecosystems. We wanted to see how they're scale dependent and how they differ between the wetlands. So we first look at individual characteristics of wetlands, such as wetland type, wetland area, wetland catchment area, incremental catchment area, so areas that drains in into the catchment. And also we looked at the ratio between the wetland catchment area and the wetland area to kind of understand, well, a through flow. We also wanted to see, well, what about the large-scale processes and ecosystem services we might find in wetlands. So we looked at two ratios, the ones here, or index we can call them as well. And so basically is summing up the wetland catchment areas and try to see how much it covers the wetlandscape. And the same with the incremental. So just to show you the difference between the catchment area and the incremental catchment area. So here first we have, in the A picture, we have two wetlands with their own catchments, and here they're overlapping. So if we sum them up, this area will be counted twice. And because of that, so if we sum them up and divide it by the wetlandscape area, we might get an area that is larger than the actual wetlandscape, so more than 100%. And in the other case here, the two incremental catchments are more puzzled, so we don't count this area twice. So in that sense, if we sum them up, we might have an area that is equal to the wetlandscape area or less. So what about these characteristics? For instance, wetland type. Well, here we found 10 different types. What we could see is that in the small wetland catchments, we find less variety of types, while in bigger catchment wetlandscapes we find a larger variety. And also some of these types also showed quite large, in average, large areas, which can be interesting in the biodiversity support. And also one part that is interesting here is that we have some types that are common, such as bog is very common throughout the wetlandscapes, and also mixed mire. So what about the areas then? So here are box plots showing the distribution or the spread of wetland area. So basically what we can see here is that we find large wetlands in large wetlandscapes, and the variety of the different sizes is larger than compared to small wetlandscapes. And this is also true for the catchment areas, so it kind of follows. So large wetlands have large catchments. And that we find that in the large wetlandscapes, while in the small wetlandscapes, it's the opposite in general. So what about the ratio? Follows the same things more or less. So in large wetlandscapes, we have wetlands that has higher through flow because their catchments are larger, which is not really quite the same in small wetlandscapes. So it kind of differs from wetlandscape, the characteristics of wetlands. And this is interesting. So what about these ratios telling us something more about the flow, the water runoff of the wetlandscape into wetlands? So the green bar here will show the incremental catchment areas coverage in relation to the wetlandscape. And in small wetlandscapes, it's small. So for instance, if we look at Berg here, which is one wetland, it's called Berg, we see it's less than 10%. So it means that the very small fraction of that wetlandscape's water will go through one wetland. Not that much. And that also follows for the blue bar, which also gives you a very small ratio. So that one actually tells you about the overlapping. So here we don't have so much overlapping. Well, but this changes through the sizes of the wetlandscapes. And in the large wetlandscapes, we have the green bars close to 1. So, well, almost 100% of the total flow in the wetlandscape goes through at least one wetland. And the blue bars will tell you that it goes through more than one wetland. So, for instance, here, we can see that the area is 4 times bigger, the wetlandscape, so might indicate that it might go through more than 2 or 3 wetlands. So what can we say about these characteristics in general? What can this show us or tell us? Well, first of all, we can see that there are differences in ecohydrological characteristics between the wetlandscapes. And it kind of is also scale dependent somehow. A key point also is these incremental areas where actually the fraction of the total flow fronted to one wetland was very low compared to large wetlandscapes. So the previous slide was the green bars. And this tells us something that we can not only look at a map and see where the wetlands are located or the density of the wetlands to tell something about the large-scale ecosystem service delivery we might get. So this is one interesting part. And then if we look at the blue bars telling us, well, that we have a funneling of water flows through many wetlands, can give us some kind of idea of what type of, well, ecosystem service we can get in large wetlandscapes, for instance, in terms of water quality, nutrient retention. So the diversity of the type of wetlands was varying between large and small wetlandscapes. But this also can tell us that large wetlandscapes contained large wetlands and had larger ratio. So in terms of biodiversity support, this might be very interesting. And in terms of any kind of nature-based solution of wetlands as well. So so now we have seen this characteristic that can tell us something about the large-scale functions and ecosystem services from wetlandscapes. But it is the concept of wetlandscape is also interesting in terms of management. At least in Sweden, the Swedish Environmental Agency is working a lot and have been given a lot of money to work with wetlands and restoration and conservation and so on. And I think this perspective might be a good base of work to kind of look, well, what type of wetlandscapes do we need to go into? What can we see here? And what can we do about it if we need to do something about it? So I think this is very interesting, and especially maybe in areas where you have lot of degradation of wetlands or loss or somehow, or even if you were talking about restoration of wetlands. Yeah, that was all, I think.
Thank you very much, Iman. Yeah. We have time for 1 or 2 questions.
So you mentioned that you believe the larger wet landscapes have greater filtration and maybe greater retention, but do you have data on that? Are you okay? Are you working towards getting the data?
Yes. So this is basically a start. Can give us some indication more or less. But of course, I think it would be very interesting to actually go in and access data, and yeah, that's the next step.
I know in biogeography in general, species area, biodiversity area relationship scaling laws play a big role, and so these are well studied for islands and so forth. But I was wondering, are there good numbers for, say, species area relations for wetlands? If one was looking at biodiversity that way, it would be a natural way of addressing the issue of size thresholds.
I cannot tell you for sure. I am my basis in hydrology, so I'm not sure.
Okay, I think it's time for lunch, and we have to say thank you again to all speakers.